We have Andrew from Microsoft back again. It took me a while to convince him to come to multi-core world, but once he got convinced, he started to come year on year. So follow the example.
So, like most of you, I get harassed by Nicholas for a talk for the title, for the presentation title. And 3 months ago, 2 months ago, whatever it is, I come up with this title I think will sound really interesting. And I'll defer the writing of the actual content until significantly later. And then I look at it last week and I think, what idiot came up with this? Me, unfortunately. And so I'm going to talk about the role of integers, binaries, grayscale, and large-scale supercomputing infrastructures. The tyranny of it, well, I guess you make your own judgment as I go through. Just for some context as to where I fit into this. So my day job in Microsoft, I'm part of the engineering group that plans, builds, and designs the supercomputing infrastructure, along with a whole load of other things, but in particular in the context of this, the supercomputing infrastructure that serves everything from general purpose HPC workloads or traditional HPC workloads through to the AI model training, but also the running of the inferencing use of those AI models as well. And so when Dan talks about Microsoft spending billions and billions of dollars on AI, it's my group that's doing that. And I mean, you can tell from the accent, I guess, I'm based in the UK. I work from home in the UK. And Microsoft is still very supportive of a work from home culture, certainly for most of the company. And I just have a rather long commute to the office when I do need to visit the office. So, floating point. We think of supercomputing as a floating point, right? That took quite a long time to generate that image. You'll see there's a lot of images in this. So I mean, there's a philosophy about this, about at which point it becomes you are the artist creating art with AI-generated images. Because it doesn't just turn up like that. You have to use a lot of judgment, you have to use a lot of iteration, you have to steer it to get towards you want. And so you do feel like the creator and the artist. You're not just blindly handing over to a machine, creating an image, and you get something perfect the first time. That took a while. But we think about floating point and supercomputing as being synonymous. Supercomputing only happens with floating point. That's the only thing that matters around supercomputing. And likewise. Equally, we think, and Dan touched on this a little bit, supercomputing means FP64, right? And if it's not FP64, it's not supercomputing. Certainly when you're thinking about planning and deploying and operating supercomputing infrastructures, it's not the FP64, indeed floating point at all, that drives your thoughts. It is integers, and this is a bit of a force, computing quanta rather than quantum computing, but by which I mean quantization of things, and broken booleans. Things that you assume are only true or false, when you start to test them at scale, it turns out to be broken and you can't use a binary or a boolean to describe them and so on. And fundamentally, what we're trying to do with these large supercomputing infrastructures, and a lot of this is independent whether you're building a large AI system or a large supercomputer for traditional modeling and simulation research, is you're trying to fit as much stuff into one of your constraints as you can. Now, your constraint might be the physical size of your data center. It might be the available power you have. It might be the available money you have. But you're trying to fit things into some kind of box. And usually it's multiple boxes you're trying to optimize towards. And it's a case of, we need more GPUs, please, as many more as we can get. Let's try and wedge as many as we can into the data center, or whatever technology is. But this is where the integers come in. You can only have an integer number of GPUs. You cannot start cutting your servers in half and fitting in half GPUs around to use up the extra bits of electricity and so on. And it's not just the GPUs that come in integer amounts either. So let's kind of run through a bit of a thought experiment. How many GPUs can you fit into a medium-sized supercomputer?
That's me.
Thank you, Dan. Yes. So how many GPUs can you fit into a 100 megawatt supercomputer? Is that legible? I'm not sure that font might be a bit too small, actually. So let's assume 1.25 kilowatts per GPU. It's an arbitrary number. I'm not giving you a statement about a future GPU power or anything like that. It's because it's a nice little divisible number. So in theory, you've got 100,000 kilowatts. So you have 100,000 divided by 125, you've got 80,000 GPUs that you can fit into your 800 megawatts. Not quite, because these GPUs don't just turn up in a bucket and you pour them into the data center, they turn up in servers, and then those in turn turn up on racks. So 72 GPUs per rack, that's 1,111 racks. So you've already lost 8 GPUs, 79,992 GPUs you put into it. Now, of course, what you could do is add an extra rack and just put the extra GPUs in that rack so that you come back to your 80,000 you can afford to power. But the problem is you've now created an unfortunate asymmetry or inhomogeneity in the interconnect, the cluster as a whole. That may not be a problem depending upon your workloads, but for some workloads, particularly anything that's trying to use large fractions of the system or the whole system, having that asymmetry can be a significant problem. So you don't want to do that if you can help it. And now let's assume there's some technical reason why you want to not just have a single rack as your building unit, but you want to have a building unit of perhaps 8 racks. For example, you want NVLink domains or some other thing like that. And also, there's no reason why you want to deploy these things in pairs. So sort of sets of pairs of sets. And so you end up with a basic building block now of 16 racks is the lump. And suddenly, you've got 79,488 GPUs. So you've lost 5,000 GPUs. Or in other words, you're wasting over 0.5 megawatt of your available power. And so you see where the integers start to come in, that you're not maximizing the resource you have available because you're trying to fit these things into the integers available. Now, some of this is driven by power, but it could be driven by other things as well. It might be your interconnect topology. We'll take a very simple example, a very smaller scale system. If you've got a 72-port switch, you can connect 72 servers to that switch. And the moment you decide to expand it to 73 servers, you now need another switch, which is also now taking up power. So now you've got less power available for the 73 things you're trying to connect to it. So maybe you're back to 72. And so these boundaries around the data center design can cause some challenges about how you architect the bigger system, how you fit the most stuff in. So in this example, what happens if we change the numbers? So one of the things you can do is to back off on the amount of power in each GPU. So let's say, for example, this is not at all legible, is it? It's perfectly legible on my screen. So we're going to have to talk you through it. So what it says is, imagine if we clock it down to 1.0 kilowatts per GPU. So now you've got 100,000 GPUs, 88 racks, if you were just looking at the racks, but if you work your way down the bottom of this page, same calculations, you've now got 99,072 GPUs. So you've got more physical GPUs, you're wasting 928 kilowatts of power, so you're wasting a megawatt, and you've also got an additional challenge. This is the difference between designing a slide for use on a screen versus a projector, because some of these things look really great on the screen, but they don't look great on a projector. And hopefully the text will appear at the bottom, which it's not. There we go. So you've now got more GPUs, but of course you'll reduce the power of those GPUs. And so does more GPUs at a lower power versus fewer GPUs at a higher power end up with better application performance? And this is a trade-off you've got to figure out because you're trying to fit stuff into this data center. And if you just take this really simple example and you plot it out, and so you say the amount of power per GPU and the amount of wasted megawatts along the two axes, it's not a linear curve. It goes up and down in non-obvious lumps as you fall over integer boundaries and into modular boundaries, I guess. And so finding the right pocket where you can maximize the amount of stuff you can put into that 100 megawatt limit is not a case of just trying the extremes. You've got to look through what's causing those limits. And you've got to figure out whether you can break those limits. Because the real question is not how can I clock the GPUs up or down to figure out how many I can fit into the space, nor is it about how many can I fit, how much kilowatts am I wasting at the bottom. The real question is 100 megawatts really the limit, or do I actually have 101 megawatts and I can fit a load more GPUs in to get it back up to the number? Can I add, or is it actually that I've got, whatever it is, a 99.1 megawatts, and therefore losing the megawatt at the bottom, or the 0.9 megawatts at the bottom, is not a problem, because that's actually what the data center is. We make assumptions about our data center limits. We make assumptions about our dollar spending limits. We make assumptions about our physical data center space. And quite often those assumptions turn up as rounded numbers because they're easy to write down. We say our data center space has 100 megawatts, but often that's a rounded approximation. And so part of what I'm saying here is about figuring out the integer limits in the system design. And part of it is about figuring out the things you thought were a limit, what if they weren't a limit? So for example, if your suppliers have only got so much factory space and they can only manufacture so many entities, whether it's GPUs or NICs or server blades or whatever it is per year or per month, and you need more than that, traditionally you would have thought of that as a hard limit. What happens if you buy enough of them that your supplier can now afford to build more factories, and suddenly the manufacturing production rate is no longer necessarily a production limit? Or you're running out of acceptable non-carbon generating power in the world, so you stop building, right? No, you start to look at other things like reopening nuclear power plants and stuff that Dan very kindly mentioned earlier on. Or you start sponsoring the production or the research into small modular reactors and so on. So what happens if you start removing the limits that you thought were limits? And we talk about this stuff in terms of the big supercomputers. So there's this clip that went viral a few weeks ago when the 500 billion Stargate project was announced, and our CEO Satya got on an interview a couple of days later where he managed to get in what was, I'm assuming, a prepared soundbite, which essentially says, I'm good for my 80 billion. We are going to spend 80 billion on AI infrastructure this year. And so the thing with the AI infrastructure build out is we're not going to build an $80 billion supercomputers. There are limits to what we will do, even what we will do. So it's not an $80 billion training supercomputer. There is large training supercomputers in that number, but a lot of it, and to borrow our friends at the top 500, this is the position in the top 500, this is a relative performance, and I'm sure you're all familiar with the fact that it's an elbow, and there's all of the performances here, and all the number of systems over there. There's an interesting zone in the elbow there we can talk about later. But the key thing with that investment is not necessarily building the largest supercomputers, and you can make your own deductions about what I mean with that arrow. It's the fact that you're building a lot of supercomputing infrastructure here to run the inferencing, to actually run the usage of the LLM models, or to run the usage of the Gen AI or whatever it is, rather than just training them in the first place. And all of this infrastructure is itself supercomputers. It's not run on generic commodity cloud hardware. You're building out decent sized, we won't be specific about it because this is a public talk, but you're building out decent sized supercomputers, many of them around the world, to deploy that, to actually run those infrastructures. And this is, again, another integer part of when you're trying to figure out the supercomputing infrastructure design. It's not just a case of, can you build one of them? It's how does that same design philosophies, how does the stuff that you're doing with the design of the systems, the design of the clusters, the design of other things I'll come on to in a minute, how is that replicable or not, 30, 50, whatever it is, times around the world in different infrastructures. And in particular, this is, again, I'm not quite sure where this text is coming out. This is a pretend image. This is not a photo of our next-gen data center. But it's that build out of that infrastructure and how many you can afford to have. But you have integers here. So it's not unreasonable that at some point in the future, supercomputers may span more than one physical data center. So how do you start to think about things like that? Because you're no longer talking about whether I'm going to spill over into one rack or two racks or n racks. It's a question of, are we going to have one data center, two data centers, n data centers for the size of the supercomputer? So there's another big integer challenge coming at some point. Okay. You remember when HPC was really simple and everything cluster was broadly speaking the same? It was an on-prem cluster. It was a CPU, an x86 CPU, probably an Intel CPU or AMD, depending on which era you're in. And it was all connected by InfiniBand, broadly speaking, unless you're buying a few niche machines. And we as a community decided we didn't like that. We wanted more choice. We wanted competition and diversity in the ecosystem. choice is one of those things. It's nice to have in theory, but it's a right nuisance when there's too much of it. And if you're trying to design supercomputing infrastructures, particularly a long way into the future, this is what we ended up with because we wanted choice, right? We wanted diversity and competitive pressures in the ecosystem. So now when you're designing a next-gen infrastructure, are you going to be CPU-based or GPU-based or a mixture of the two? If you're going to be a CPU-based system or if you're going to have CPUs in it, which we all are, then you're going to have a mixture of those choices. There's a lot of choices for GPUs. You've got a choice of where you're going to stick it. Your data center, somebody else's data center. You can operate it in a cloud style. You're going to operate it in a traditional style. There's interconnect choices now and certainly out into the future that I'm thinking about. Different memory technologies. Storage is worth an hour's talk on its own. And what level of computer you're going to use, full fat, FP64, or various flavors of low-calorie computing, or even non-IEEE standard, IEEE 754 stuff. And the key thing about this is that A, you've got to make your way through this design space. But again, it comes down to integers. Can you only support one configuration of these things? Or can you support 2 configurations, or 3 configurations, or 4, or n? What is the n that you as an organization can afford to support? Now, if it is strategic for you to be able to have a reasonable managed risk in the future and your organization is heavily dependent upon the success of your supercomputing initiative, then you probably don't want to navigate a single path through this. You want to be able to have more than one path through some of these things at least. Not necessarily covering everything, but you probably want at least a second path through some of them. And so potentially you're supporting 2 configurations, deploying and supporting 2 configurations, and this is even before we get into talking about what you do at each generation as how these things evolve. But how many can you support? What's the n? What's the number of integers you can sensibly support as different versions of this infrastructure? That's a non-trivial optimization problem as well when you're trying to figure out where all of those billions of dollars go. And then one of the other challenges that you have with, I'm just going to put this down, with supercomputer design, I said I was going to talk about planning and operating supercomputers. Operating supercomputers comes down to SLAs. A typical reaction when you start talking about SLAs to a bunch of technical people, and this is true within any organization, ours is probably the same as yourselves, is something like that. SLAs, okay, can we just deal with that later? But it's not, it's part of the core design.
Yeah.
It's part of how you design the infrastructure, it's part of how you figure out choices between A and B, and again, it comes down to, this is when the broken booleans comes in. You think of things as by either being up or down, or working or not working, and at some point, that's a false assumption, a false way of thinking about it. So surely it's just a case of building a 5 nines infrastructure, 5 nines data center. 5 nines is really good for a lot of use cases. So for high-value mission-critical services, which includes plenty of applications for HPC, weather forecasting being an obvious example, there are others, it costs money. I mean, for some things, it really does work, but it does cost money. It's not trivial. It's not cheap to implement highly available HPC services. And extreme use cases such as AI training or LLM training stretch. 5 nines in itself is not enough for that. So why? Traditionally, a machine, and this is kind of used internally, so everything says virtual machine, but we can think about it ourselves in terms of a node. A node is either up or down. So if the node fails, the workload can be migrated to some other node, or if the primary node fails, you get into an alternative cluster, potentially, if you have, like ourselves, multiple clusters around the world. But imagine you have a node with multiple GPUs in that node and multiple InfiniBand NICs in that node. And now you imagine a multi-second or even a sub-second transient glitch on that node, on a single GPU within the node, or a single bank of memory, or a single NIC, or whatever it is. The virtual machine will still be up. So it's still satisfying. 5 nines is all good. This thing is still satisfying 5 nines because the machine hasn't been taken down. It's degraded a bit, but it's still up. But it's likely that any large job running on that system, especially if it's a whole system job, will be interrupted and probably fatally. You'll probably kill the job. So your traditional measures of availability and reliability don't necessarily apply to this context. And then you get one of the other things we traditionally don't do a lot of in the HPC world, but is traditionally done a lot of in the cloud environment, is you're carrying hot spares. So when we make a cluster available with 1,000 nodes in it to the Azure customers, typically there's whatever it is 1,000 plus 20 nodes physically in that cluster, and we allow for the fact that a percentage of them aren't going to be working at any given time. And so that makes sense at smaller scale, and it makes sense when you're repeating that capacity around the world. But if you're starting to build single larger supercomputers, then all of a sudden you're carrying off, you're wasting potentially a lot of your power, a lot of your physical space, a lot of your integer planning. Remember before about network boundaries and topology boundaries and so on. And you're wasting a lot of that capacity just sitting there waiting to be used when the rest of it falls over. So it's not doing useful work. But then you've got to balance that out against the probability of the whole cluster becoming non-functional. And so when you multiply out $80 billion and you assume a certain amount of time for that to reduce the return on investment and so on, you can end up with numbers like a couple of $100 million wasted per day of downtime. And you can divide that out into hours and all the rest of it yourself. So maybe actually spending a little bit of hot spare works, but finding the balance of that ratio is non-trivial. That's far from trivial. I was going to get in a comment about 1 exaflops being with the S on it. There is no such thing as 1 exaflop, but we haven't got time for that, so we'll move on. But there's this question floating around on social media over the last couple of days, partly prompted by a question from Hyperion, who are doing a study about this. And the question is, and this kind of, I've stolen this to lead into my final point. When will a hyperscaler take the #1 spot on the top 500 list? And I think the options were this year, next year, 5 years away, never. In the room, we'll have a live vote in the room. Who thinks the hyperscaler is going to take the #1 spot this year? Next year? Within 5 years? Never.
Yeah, we're going to spend money to have that kind of.
So there's 2 implicit sub-questions here, which you can get into, Jeff. When will a hyperscaler have a supercomputer, with some caveats on what that means, capable of taking the #1 spot on the top 500 list? And you can leave that as an exercise to yourself whether that point has already been passed or not. And then number 2, when will the hyperscaler choose to list that system? And so I can't speak for everybody, of course, but I'll give you a view from the hyperscaler who currently has a #4 system, has previously had a #3 system, or that same system, and is probably the target of that question in the first place, given whether any hyperscaler has played that game. And this might be the reason why this talk doesn't, the recording of this talk may or may not get published, depending on what you can incite me to say in the next few minutes. But the reason we do it is that so when we build supercomputers in the HPC community, we deploy the supercomputer, we get it up and running, we do test and development, we do acceptance testing. Part of acceptance testing, we run a top 500 run, and then we put the thing into production. That's a lot of wasted, valuable time while that system is being built. So when the first few racks that are being built, they're up and running, they can be doing something useful, but no, they hang around until the rest of it is built. And then hang around until even acceptance testing, and then you put the thing into production. Your, whatever it is, $100 million grant for that system, a good fraction of that is being wasted when the system's available. Now, if you're only building a 5-rack system, then you don't lose much time because you can build those 5 racks pretty much at the same time. If you're building a 1,000-rack system, then you're not going to build 1,000 racks in a day. That's spread out over time. And so what it means is that at some point, if you've got a big enough system, it's taking a couple of months to build the system physically, and before you get into any kind of acceptance, it makes sense to just get those racks into production, delivering science or delivering training or delivering inferencing, whatever it is, as soon as they're ready, and not wait for the rest of it. And that's fundamentally the reason why we're unlikely in the future ever to take that #1 spot. Not because we can't afford to do the run, because we do the runs as part of the engineering burn-in and part of that testing procedure. We do HPL runs. But because we're never likely going to hold the whole cluster back to do it when we can already put some parts into production. Once it's in production, it ain't coming back out again. So I'm not saying never. I don't want to be held to never. but it's unlikely the way we choose to operate now. It's just become unlikely. So the reason that the Eagle system was listed last year is because it was a contained deployment unit that we built that it made sense to run it on, and the deployment units are just smaller now than they were at that point. So that was the fraction that was deployed and ready to go at one time of the over a bigger machine that it was actually a part of. And as I said, those physical deployment, our ability to get something into service at smaller scale and quicker is improved now. And so I'm going to close with this slide. So there was Dan's talk earlier talked about what the AI community can learn from HPC. So I'm going to return the favour a little bit. Some of the things that we can pass back on. So some lessons, hopefully. Getting stuff into earlier science. With the traditional all or nothing model of supercomputer build out, getting a whole thing system ready before we put it into production, before we do science, maybe that's something that we don't do in the HPC world in the future either. We look at how we start to get the system into production. We'll have to give up on the top 500 list, or at least taking the big box on the top 500 list, but maybe starting to get those big supercomputers into production delivering science earlier is worth backing off that a little bit. One of the things I didn't quite pull out through when I was talking about the SLAs, it turns out in our experience that sacrificing a bit of performance, so backing off on the amount of dollars you spend on the most performance and putting a little bit of that in reliability, increases your overall time to solution. So if you have a amount of science you want to achieve, or training a large LLM, for example, it turns out that spending a little bit more money and a little bit backing off on the performance to get a bit of reliability gets you that time to solution, gets you the overall science delivered in a short amount of time frame. So again, there's something that maybe we need to look at in the traditional HPC community is go and revisit some of those notions about reliability and performance. The design space is not a continuum, nothing new there. Anybody who's been designing HPC infrastructures knows that for a while. I think the things we're really starting to learn is that the performance curves are significantly non-linear. There's weird pockets of optimization in them. And remember that people come in integer quantity too. You can't have half a person. Well, not in a sensible way. And the other thing I want to say is hard constraints. The things we've traditionally thought about as hard constraints might not necessarily be as hard as you thought they were. We make easy assumptions about what our constraints are, but actually genuinely knowing which of your constraints are hard constraints versus which ones are just difficult constraints is not something that most supercomputer centers are good at. Now, my supercomputer has to go into the data centers that happens to exist in my local place or even my country is not a hard constraint. And there are supercomputer centers I'm aware of around the world who are actively looking at placing their supercomputer infrastructure into another geography because it gives their supercomputer center the ability to stay around for the future, essentially. Bearing in mind the supercomputer center is about the people and the science and the support it does, not necessarily the hardware. And there's a lot of stuff else there. I think the other thing I'll add is that I did write this before Dan wrote his talk, this line, but we are actively interested in collaborating with the HPC ecosystem to find out how we can both benefit. Thank you.